Hi, I'm Alan Ross, and I am the managing editor at Transformer Technology, Power Systems Technology, and I am a co-editor of Women in Power Systems. But our guests today to go through this webinar are two people I know well, and you're going to get to know them very well. Bob Razor. Bob and I worked at SDMyers, and even before I worked there, we brought SDMyers and a company called Sun Ohio together. I've known Bob for about 20 years now, but Bob, how many years have you been with SDMyers?
Working on number 48.
Okay, that is unheard of. You got to get to 50, okay, because that's kind of cool. Wesley, years ago, I hired Wesley, a young man, and he was an intern with us at SDMyers, and now he is permanently with us at SDMyers with 3 children, a beautiful wife. I actually went to his wedding, so I kind of know what's going on. But Wes, how are you doing?
Good. Thanks for having me.
You're working on your first, what are you now? You get to count the intern years.
So Bob has 48 years and I have
47, but
okay. Yeah, actually, no, I'm working on year number 9 right now.
Excellent. So the topic we're going to be talking about is maintaining aging transformers. One of the problems we have right now is you can't get transformers fast enough, and that's not going to get fixed, especially in the United States, in a very short time. So maintaining your aging fleet has become more important for utilities. It's become more important for industrials and commercial, because if you can't get new transformers, you need to make sure that the ones that you have are working better. And interestingly enough, I know that we've been through some things. We had a birthday about 5 years ago, and it was a birthday for all the transformers that SDMyers monitored, did testing on, and it was 100-year-old birthday. I think we had 6 of them, right, Bob? That was crazy. So from somebody who really understands aging transformers, understands reliability, understands sustainability, that's Bob Razor. So Bob, if you take it from here and talk to us a little bit, and you're going to hear me step in because there's some things that you're going to say that I want to clarify. But Bob Razor, go ahead.
Yeah, we'll start off with a few introductory. First of all, good morning, good afternoon, wherever you are. Great to be here. So just we'll start off with some definitions. Why are, aging transformers? What are the similarities and disconnects between not aging ones and aging ones? Realities from a large data source. So we're going to go through a plan too, as well as how we can watch over our aging transformers. What's different than the ones that are not so aging? And then some conclusions. It's pretty simple format here, and we'll start off just with some general knowledge of transformers. They're all over the place in terms of size and function, but there are some common factors. They were designed to operate for 30 to 40 years, and many of them are much older than that. And the average transformer, we've got some data to show that. We've got quite a large database here that Wesley's done some data mining and some preparation to share with us. What's common in general? Well, they obviously age, and the life of the transformer is the life of its insulation. Pretty well accepted fact. There are some things that can interrupt that, some acute, happenings that aren't always a part of the things you can do proactively. But reliability, by definition, for a transformer is the assurance that it can operate without failure for a certain amount of time under its required operating conditions. We know some things about failure rates. We need to know present condition, what's changing about its requirements, and then how quickly is it, it's important to have a resiliency to your system, and that includes spares and ability to replace one or to get it switched out if you have a spare.
A quick note, that slide that you just showed, and it said changes in operating conditions, for a lot of different factors, one of the things that is happening, whether it's a utility, industrial, or especially a data center, is that they're running hotter. They are running them at temperatures for periods of time. And I say they, I'm talking about transformers in general, in every country. Their operating conditions are getting significantly more dangerous as they operate at higher temperatures.
It's true. Good point, Alan. And of course, we have ways to watch that we'll touch on. That's a part of, extending the life of the transformer. So with what is in the background behind this sharing with you folks is that we've got a lot of experience, hundreds of thousands of transformers. Wesley's going to touch on some of this, millions of data points. We are involved in ASTM, IEEE. We're familiar with the safety guide from NFPA 70E, and then of course the maintenance guide that's been newly updated, 70B, touches on the things we're going to talk about. What are the things that make a transformer different, in terms of an older one versus a newer one? Construction quality, the copper versus aluminum windings, the load the transformer's on, the maintenance, and the type of insulation. And that's going to, as transformers, we run into the older ones, you're going to see a difference, a break in the way they were wound in terms of insulation type. So, Wesley, explain what you got here.
Yeah, so Bob asked and invited me to corral some data that we have in our systems to help articulate and, have this conversation comparing and contrasting in-service, newer manufactured units compared to aging transformers. And first, I'd just like to step back for a second and say, this kind of conversation has entered the more national mainstream conversation. And Bob touched on it in a few different ways, but, even J.D. Vance was noted emphasizing the importance of the electrical infrastructure, transformers specifically, for a number of different reasons. The manufacturing ability of America with the grain-oriented steel, the applications that transformers are required to power these days. So I think the conversation, SDMyers obviously has been around for a long time, since 1965. This is our business. We find it important day in and day out. But what's interesting is this conversation has become more important, specifically in America, which is interesting context. So the word aging might mean different things to different circles. So if you're in the transmission circles, Doble releases a failure statistics paper. You have reliability papers from Seagray. I'm gonna compare those different populations of data to our population of data. So our population of data, when we mean aging, we'll reference it both on the conventional definition of aging, but then also our definition of aging. So we looked at the in-service age distribution within our population set. So those units which we're inspecting and testing. And to orient you to the pie chart on the right, the dark blue is the less than 10 years old. The orange is between 11 and 20 years, and so forth. So the let's split the chart in half. Let's just look at the dark blue and the orange. If you look at the dark blue and the orange, that's about 50%. 50% of our in-service inspection and testing is completed on transformers that are less than 20 years old. Comparatively, the other half of the chart, the dark green all the way up to the light green, is 20 years and then even over to 50 years old. So when we talk about aging, our population of data is generally now 75%. So the dark green, orange, and dark blue, about 75% is less than 30 years old. So that's just the context, setting the stage for what do we mean when we say aging. But let's compare it to the next slide, which is, and again, Alan mentioned this earlier, but just to have a little fun, we combined all of the transformers that are 100 years old or more that have been tested in the last couple years. And what you'll see here is a couple single phase units. I think a couple of them are manufactured by Westinghouse. So these would be units that are older than 1925. And I think, yeah, it says right there, 15 of the 24 have been tested in the last 12 months. So I want to compare and contrast some things about newer and old units. Obviously, just because it's old doesn't mean it's deteriorating. Just because it's old doesn't mean it's unreliable. There are some special considerations that you need to consider when you look at older units. And so I've hoped to articulate one of those considerations in this chart. Let me set the scene for this chart a little bit. SDMyers, like some other grouping systems, we group transformers into 4 categories at the highest summarized view. And those categories are a health index score. The health index score, the category 1 is satisfactory. Category 2 is a watch condition, which might mean decreasing your intervals for testing, but generally it's in good condition. But the third category is a service recommendation. And then the 4th category is at risk. So what I wanted to show is I wanted to compare using these same groups of transformers. So again, on the x-axis, you see less than 10 years old, all the way up to over 50 years old. And I wanted to compare those categories. So the green line being the satisfactory. This is health center score number 1. This would be akin to IEEE's 4 conditions that they have. It's in the same direction as that. And you look at the paper health over these buckets and in these 2 segmented categories. And what you'll see is that although there is some paper degradation as transformers get older, just because a transformer is older doesn't necessarily mean, like I said before, it's not unreliable. And you need to be particularly concerned about transformers that are both older and have abnormal testing results. Comparatively, newer transformers or comparatively older transformers that have healthy testing results or newer transformers that have abnormal results, you need to be a little less concerned with the factor of older units, abnormal test results. And this highlights 2 things. First off, that the life of the transformer is the life of the paper, but also there are so many different components of a transformer that you need to monitor and maintain that it is not just the life of the paper you need to be concerned about. That would be like somebody saying, it's just your heart health you need to be concerned about. Well, there's a lot of other health factors and characteristics that you need to monitor, maintain. And then I'll kind of just explain this chart one last time before moving on. But it shows that as the transformer gets older, those that are in the at-risk category, the paper health, as presented by the estimated life remaining, decreases considerably, 15% or more. But it is all other factors that also combine to make that transformer in an at-risk category. Like I said, the active faults, leaks, bushing conditions, gasketing conditions that you need to to monitor and maintain. And then one last idea to kind of set the scene for how are aging units different than newer units. I wanted to present how components change over time. So one component, if you will, of a transformer is the liquid that fills the main tank. It covers the core and coils, providing an extra layer of heat distribution. And the chart on the bottom left here shows across manufacturing years. So on the x-axis, we're going to start in 1960. We're going to go all the way up to 2023. The dark blue shows the presence and the prevalence of mineral oil in transformers. And over time, the fluids have changed. So in the 70s and 80s, silicone became a little bit more popular for units that are either indoors or close to buildings. The purpose of that was for fire mitigation. It's got a higher fire and flash point. And then what you'll see is this purple bar start to come into as a proportion of the number of units. And the purple bar the purple area is showing FR3. FR3's natural ester manufactured by Cargill. And that is about, it's taking a portion of the mineral oil over the last 20 years that are on newly installed and newly manufactured pieces of equipment. And again, the same kind of ideas for why FR3 is popular. It's got a higher fire and flash point. It's more resilient to moisture. It can hold up in a lot of operating conditions. So there's a lot of benefits there. But the point is that I just want to show how aging units have original components, more or less. Original gauges, original bushings, original gaskets, original fluids, original paper, even paper that might not be thermally upgraded. So this is just one example to show how components change over time and how we're not trying to articulate one as bad and one as good necessarily, but how you need to consider those components in how you maintain them, sample, test, those kind of things. And then, like just the design and style of a 1960s era model. The radiators are different than what we might see today. The style is different. And now a 75 MVA or 7500 kVA unit may be a cabinet style design with the panels that you open. So just articulating the differences between an older unit and a newer unit.
So thanks, Wesley. And
Let me ask Bob a question.
make any comments, sir?
Yeah, there's another area. When you think of newer units, today, when transformers are made, when they're specified, they are built to specification. They're built right to what they're supposed to do, which is a 20-year life. You mentioned it's 30 or 40 years. Today, they're built for 20 years. That's about every manufacturer that does it. The issue is when these aging transformers, Bob and I remember the days that we used slide rules. I mean, when we designed these things, we put an extra measure of robustness. You mentioned Westinghouse. I think probably the best transformer ever made was in 1976 at the Westinghouse plant. They overbuilt it. And today they're not overbuilding them. So it's not just maintaining transformers over 20 years. We need to start with the ones that we've got now so we don't get to the point that aging happens too critically. But would you agree that transformers today are made differently? They meet the standard, but they're made differently than they were back in the 70s and 80s?
Or computer design, they've got the liquid percentage, drops. The gallons per kVA are down lower, better designs. This is dovetailing right into these next couple comments here. And in 1970s, paper, insulated, thermally upgraded paper made a difference. This helped aging in some respects. The older transformers tend to create purans as a good indicator of knowing how the aging process on the insulation goes. That can tie directly to the remaining life in the transformer. Some more cons. Older transformers have decades. We have decades of data. And there, again, is the Furan comment, transformers over 1,000. Now, that's parts per billion. They've lost considerable life. And once you do lose the life through oxidation, through moisture, through overheating, you cannot restore it. So it's a good thing to keep up on it. That's part of our content here today. Electrical testing, another great thing to do to transformers. And FPA 70B says 3 to 5 years. Insulation power factors are a good indicator of the condition of the insulation system. That includes the liquid and the paper. These are some of the things that we're always chasing around to improve the transformers in the field service world. Gauges, cabling to fans, leaks, pushing condition, all a part of the cons. Older units need attention. Gaskets, again, LTCs. I've got a little bit more data on LTCs later, but they need to be addressed as well with inspections that are somewhat different than for the transformer. Paint can also be a problem, especially on the radiators. So here's the practical steps we're going to go through pretty quickly here. Having your catalog, having some type of a way to assess transformers at risk, moving toward being at risk. We call that the service category in our model. Make sure you act on the ones that are at risk. And then number 7's pretty big deal, backup spares, however you have your means of, assuring power if the transformer does have a problem. There's an example, some cataloging. This particular view that we it's a view of our dashboard where we show the ones that are at risk and the ones that are healthy and the ones that we're monitoring. These are the things you pick up on a visual inspection. We recommend at least once a year, but twice a year better. You want to look for level leaks, the condition of your desiccant. Free breathing transformers are becoming more and more rare as the aging process continues, and the oil preservation systems are different. Not so many free breathers. The condition of your gauge, the level gauge in particular, you want to make sure it's reading accurate. That's a combination of looking at looking at temperature and the level, just to make sure it's at the right place so the transformer doesn't overheat. When these radiators tubes become breached, the transformer is no longer cooling. You may not even see it on the gauge. The gauge could be elevated above the liquid level once it drops below the fins. Substation overgrowth. Liquid sampling. Currently, it's IEEE C57106. There's a guide similarly for esters, for silicone, for heavy molecular weights. Those documents give guidance on where transformers should be for in-service. These are some of the tests. Probably familiar with these. DGA, a great test for looking at aging of insulation. There are key gases that go along with it, and also some different ways of looking at the data, such as the triangles that are popular. Moisture's a big deal to keep looking after. Liquid power factor, also tied to insulation degradation. Infrared scanning, taking a look at the transformer from a thermal point of view, finds temperature abnormalities. The two that I'm showing here in this screen, one is a overheated conductor, and then the other would be level. You can see level. Again, if the transformer has a low level, the transformer is going to overheat, and you'll see that in the profile. Electrical testing. I'd point out, once the furans, if you're watching those, are over 2,500 parts per billion, There's some risks with testing. Not saying that it shouldn't be tested, because you may want to know, regardless of the condition of the insulation, to withstand a fault. But once the paper is weakened, and it truly is weakened, it could fail the transformer if the levels are too high in the furans.
Bob, let me use something here. We're getting questions, and this one is going to relate to what you just said. So, how should we prioritize aging transformers that have high furan levels but are still performing reliably?
That is a fantastic question, because there will be some risk to leave the transformer go with higher furans. It could last another 20 years. It's its ability to withstand a fault. And to check that better out, the electrical testing comes into play. So we do test transformers with elevated furans, electrically test them, and then can more or less say, I think this is worth keeping in service.
So it might show up watch, and you mentioned earlier a health index. One is it's working fine. Another one is watch, which might be change the testing time. Maybe you go twice a year, or and then the third category is one you probably need to do some service on it. So it's watch and act, and the fourth one is, oh my gosh, run. So if you're looking at that, where does that in that thing? Where in the health index would that transformer fit?
We're going to get into that in just a minute.
Okay,
so I'll reserve that till the slide shows up.
All right.
So here's your at-risk detail. Pay close attention to these. When the level is very, very low, again, the radiator tubes or the cooling system can be compromised to where the transformer is overheated. Major leaks, you're looking at moisture ingress and problems. If you have an active fault showing up in your gas and oil analysis, definitely recommend electrical testing. You're looking for the high temperature gases like acetylene and ethylene. We always recommend, regardless of furans, take a look inside. There could be something that we can adjust, fix, a tap switch, a loose connection. Electrical testing can confirm that further, such as your winding resistance, to tell you it's something, pointing out more carefully when you look inside what you can fix and cannot fix. Very high moisture is a problem, even to the point, and we're going to get into moisture just a little bit later, so I'll hold off on that. And then highly oxidized oil, you can stay off the effects of the acid that's created when that oil oxidized by doing oil processing. Correct the oil, try to get some of the acid formating compounds out of the insulation with hot oil cleaning.
Hey, Bob, can I interrupt here really quick? Just to, so I'm reading a few questions coming in, and I feel like they're applicable to the testing, and I felt like they might be helpful to mention here. So Michael's asking about DP, and we would align with that DP recommendation of 200. We have categories. So as the estimated DP lowers from 800 down to 200, we put an estimated life remaining. And so we align with that. We think that furans are a good interval test to include with moisture, DGA. You don't necessarily have to do a furan test every single year if the furans are acceptable, or they're not, it's 800, they're not coming back with any furans detected. However, be mindful that if you have an oil processing, or you've done a hot oil clean, or you've processed on the oil or repaired the equipment in any way, that some of those methods might extract furans from the presence of oil. So before and after field oil processing, you might want to have a furans test to have a baseline set from before and from after. And then George, what's interesting, George, we've got transformers that go less than 200 and they're still fine. And here's what I would say about that. one of the number one causes of failures are through faults across many studies. And a through fault is something that is essentially not in the normal operation of a transformer, from a lightning strike, from animals chewing on something. And so the paper is intended to withstand these very short overload conditions. But if the DP is less than 200, it's going to the point where it can't withstand these overload conditions that may or may not happen. So be mindful of that. I'm not saying, just like transformers can technically run a while, or they could run by having active faults. They could run while having high moisture. They could run while having elevated or low levels of DP. So I just thought I would comment on the Furan comments there for a minute. Sorry.
No, good comment. This slide goes without saying, not much to say there. So you acted the at-risk units. Interesting how this slide sort of cut off a little bit. But when it comes to moisture, I think it's worth mentioning that when you go to the IEEE guide that's currently in place, that's, again, 106, you're going to see that for voltage classes, they have a parts per million limit. And in this slide, center graph there, you see the shaded orange that showed this is an actual study that was done as a part of a task force that led to creating a whole new standard coming out for moisture. I believe it's due out this year. It's going to be C57 166, and it dives into, 162. 166 is the consolidation of all the liquid guides that's coming out, but C57 162 is moisture. This task force created data that led to that new standard coming out for moisture. And in 162, the 25 ppm limit has to be taken into account with temperature. And that will be addressed in 162. It was not addressed in 106. This transformer, for 20 years, we tested it every 6 months. Winter, summer. This transformer happened to be located up here in the north. We're near Cleveland, Ohio. And you can see that the ppms in the middle graph stayed acceptable throughout the winter, irregardless of the transformer being wet or not. All the way across the graph. Sorry, it's cut off there, but it stays under 25 ppm in the winter. However, in the summer, when the solubility of the water flies into the oil because the oil's hotter, warmer, you're violating the 25 ppm. The bottom graph is percent saturation. And limits in the new standard, we're going to mention some limits. 20% saturation is a good number to stay away from or try to stay under. And you can see that once the transformer became wet, the saturation jumps. A good test, irregardless of temperature, to follow when you're looking at moisture. Gas A again, very low liquid levels, excessive moisture. Put down 30% here. 20 is like the limit. 30 is really getting wet. And then oxidation is where acid is created. And the acid attacks the paper, weakens it, changes its tensile strength, increased furans, indicator of lost life, and so forth. Well, it has to get to become at risk. It doesn't get there overnight. It's something you can see. So trending toward at-risk units is our service-related category, which you can look at as being in between great and not good. What can you do in the middle? This is how you can extend the life of your aging transformers. Don't let them become at risk. Stay off the problems, such as when the level is becoming low, don't let it get too close to where you might have it overheat. attend to increasing power factor, interfacial tension, and acid by oil reclamation, keep the moisture levels low, those are the tips we would give toward keeping an aging transformer from becoming unreliable. To look at your system resiliency, have spares ready for each transformer. I think we're doing okay on time. Are we now, Alan?
We are. We're fine. Yeah.
Got five more minutes or so before questions, or 10 minutes?
Yeah.
Verify and document its condition. So the spare may be sitting there in the yard. It may have been taken out of service for a reason. It tripped offline. You saw some gassing in it. You had a spare. You put the spare in, and this other one sits over, and it possibly could be out of sight, out of mind, and you don't really know its condition. It's a great idea to have that spare looked at, upgraded, painted, whatever it would take to have a very reliable spare. And then, confirm its condition periodically. We did a study a number of years ago. It was presented in a CGRA and IEEE paper where there were 1,500 transformers that we had in our database that were decommissioned. To show the effectiveness of service work in the in-service range, perhaps prompted by the trending data showing, that it's for real, you've got a situation brewing, go ahead, perform the service. The service, from what we data logged here, was moisture reduction, keeping the oxidation inhibitor at therapeutic levels, which again, that's in C57106 as 0.3% US, 0.4% in Canada. And then also moisture reduction. Moisture reduction acid and inhibitor levels were maintained in transformers, and on the transformers that had the services performed over its life, we were seeing nearly 40 years of life as compared to 20. So in wrapping up some of the things we've covered here, great idea to have a person on the staff that is connected with someone who can help lead this with you or lead it themselves. Categorizing, taking note to NFPA 70B. It's newer in the last year or so with some stronger recommendations towards service. Again, 70B is maintenance, 70E is safety, both very important documents to look at. And then, fixture at-risk units. Repeating again, a transformer can stay in service, and you may say, well, it hasn't done anything bad yet, but it's weakened. And in the event of a surge, that's when the failures happen. Wet insulation can be dried, keeping after oxidation, performing regular electrical testing. Looking at the LTCs in the transformer are another thing to do. I'll slide on that in a minute. Larger transformers, especially if they have any kind of a gassing tendency, there are some pretty efficient, accurate online monitors now that can connect directly to dashboards, and you can look at the data in real time. They can include bushing monitoring as well as the main tank. You can do some PD work, looking for partial discharge in the tank with the bushing monitoring. LTC inspections. That's a two-faced, two pictures here, two faces. Internal inspections are obviously, taking the transformer down, draining the LTC, cleaning it, inspecting it, looking at the the contacts and seeing what kind of repairs were made mechanically. And then it can be noticed in oil testing. So regular annual oil testing is usually able to pinpoint things that are going on inside the transformers LTC. And then can't say enough about certified reliable spares.
So, Bob, that's the first question, certified reliable spares. We were part of developing for a large steel manufacturer. We developed this whole index so we could tell, these are in service that work. These ones watch. These ones you need to do some work on. And these ones you probably need to start thinking about replacing. I mean, the health index was really a good thing. The second part of that was that having a spare for every transformer. When they looked at it was a steel company, so they had vault transformers that would just surge, they'd melt everything, and then it would come offline. So it went from low load to maximum load. Those furnace units, we recommend that you have at least a spare. When we looked at the spares from this company, none of the spares could be put in service. And when the engineer that was in charge of this, put together a presentation to say to his boss and his boss's boss, we need to spend money. Like, most of the bushings were gone. They were cannibalized. Almost all the gauges were gone. Some of them were left open and just their liquid content was compromised. It was just a mess all the way. To fix that, they needed money and they needed a plan. And I remember one of the things that we did at SDMyers, we said, you're not going to fix it overnight. It's going to cost $400,000 and nobody's going to give you that budget just kind of as oh, by the way, give me $400,000. However, could you get approved $130,000, $140,000 over 3 years? And the answer was, yeah, we'll do it that way. But the engineer in charge of those transformers got, based on what you just presented, got money to be able to do maintenance, because people didn't realize you could maintain transformers, especially if you keep the oil pure and clean. Hey. I'm not allowed to say the name of the steel company, but a major steel company.
Bob, do you mind if I hop in here and answer some of the questions that we got coming in?
Sure, that's great.
So I'll go. So George asked, or David asked about DP, which is the shorthand for degree of polymerization. So to understand the health of the paper insulation, there's really only one foolproof way to understand the strength of the paper, and that would be to literally get a sample of the paper from inside the transformer. So decommission the transformer somehow, untank the core and coils, and take a sample of the paper. But we can't really do that when it's in service, obviously. So there's an online method is kind of like a secondary method to get this information. And that method would be getting a furanic compounds test, which gives us an idea of what the degree of polymerization or the tensile strength of the paper. So DP, when some people talk about DP being 800 would be the factory produced degree of polymerization that the paper comes out of the factory specified for. 800 is the highest. 200 would be considered end of life. And we go from strong, high tensile strength paper to low mush, stuff that's, like eroded and not providing any insulation. I see another question about just DGA testing and comparing SDMyers testing to Morgan Schaffer's testing. Morgan Schaffer, obviously a great lab, but they might use a different gas extraction method, what vacuum extraction or headspace extraction, who knows? I would say my comments on that would be It's more about trending from the same source over time to see how things change, because then you can use rate of change calculations that, are published in a lot of places, and absolute values. But more or less, each laboratory has, if they follow an ASTM standard, then they will have plus or minus a certain percentage of accuracy. And then there's an acceptable range of accuracy. And we're an ISO accredited lab, so we fall within that acceptable range of accuracy. So I wouldn't, in my mind, it's not as much about one lab versus another as much as are they following a method, a published method? And, are they ISO accredited to be within a certain accuracy tolerance?
Yeah, and then when there is a test that shows something that's out of sorts, the retest is really valuable there to confirm what it is you saw. And then if you still have doubts, then, send to another lab, and then you get the full picture of it and can act on it. Good point.
I forget who said this, but somebody mentioned SDMyers and EPRI using estimated life remaining. I'm not really familiar with what EPRI's most recently published on furans, but I'm familiar with the paper they published in 2008. SDMyers was a part of the paper. We offered data that they used, but I'm not certain what the conclusions were or what how we align or differ. We usually take a bucket of, we do 75% to 100% estimated life remaining, 50 to 75% estimated life remaining, 25 to 50. So we don't normally publish, like 63%. We put it in a bucket because it's not as specific as what my chart showed, which was the average in that health grouping. Bob, are you familiar with how our our estimated life remaining percentages align with EPRI?
No, I'm not, but it's something that we can look into and give some feedback.
We follow a pretty conventional model for furanic compounds testing. I don't think we deviate much from sort of the mainstream. And then the last thing I'll mention here is that Salem asked about maintenance strategies for oil cable box, especially with the GIS interface, gas insulated switchgear. I'm not as familiar with any, oil sampling protocol like you would for transformers, but I am familiar with, using other inspection techniques like you can do infrared, but then also you can do a partial discharge inspections for higher voltage gas insulated switchgear and oil cable boxes, especially when the voltages get over 4 kV on the high side, 5 kV and up. So I saw that question came in as well.
Hey Wesley, going back to the furan discussion, there's been a number of, over the years, aha moments where you see these recommendations play out and you become believers in what it offers. In this one in particular, I can recall, won't name the place, but they depended on a region strongly on the way their distribution and transmission was set up. They had double-ended subs, and they had to have both of them obviously dependable. If they lost one, this big portion of this area would have been out of power for a long, long time. So they had a double-ended sub, and one of the two transformers had elevated furans past where we felt like we should even reclaim the transformer. At some point, I think it was 3,000 parts per billion. We said, even pumping on this, it's held together even so weakly. We don't want to offer anything but go find a replacement for it. So they ordered the transformer, and before it was delivered, which took, if I recall, 9 months to get the transformer to them. This goes back about 15 years ago. The transformer failed. So now they ran on one transformer, but the other one was on its way, and then they got both. But it's just so pointed out that this furan, has meaning. And you look at other things along with it. You can look at ET again if you feel you can test. You can look at other oil qualities, power factor. It's just a good thing to always consider when you're looking at aged transformers.
But you were even saying if the paper health measured by furans, described by DP, is low enough, electrical testing could actually be harmful. Because of the voltages that you're putting it under to do the test.
That's correct.
I had a question. This is, I think this is one that we could have picked and we might have already answered, but is there a recommended threshold or a combination of indicators like moisture, acid, DGA that signals it's no longer worth investing in an aging unit? Is there some point that you just say, hey, you got to replace it?
There are. It seems, of course, I've been around a while. And when I first came to Myers, in fact, the background on my picture in this thing is Stan's first oil purifier that he built in 1965.
SDMyers.
He used to called it re-refiner of oils. And that rig was at that point around 12 years old when I started with the company. And when the transformer has an acid that is so high, again, IEEE flags transformers acid by voltage class, and the highest voltage class is, I believe, a 0.1 acid. When we see transformers up at like 0.3, regardless of voltage, we hot oil clean, but at some point, the damage to the paper, and it can be verified by furans, but the damage to the paper is probable. So at some point we say, the water content is sky high, the acid is this way. We can come in and we can correct the oil, but the damage to the insulation is not correctable. We can dissolve some of the sludge that's in the paper and stop it from being as aggressive as it might be. But once it gets so bad, it really is best to just say, hey, this one needs a replacement. And we do not see it that often. The number of transformers that we offer service to that are of that variety, I don't know if there's even a dozen a year. They're becoming less frequent. But the ones that are salvageable, helpful, we see hundreds of those.
Yeah.
And so, yeah, there's a point where you just, hey, let's look for a spare, have it ready, even replace it before it might go out, depending on the application. Again, we don't try to be alarmists, but we've got to be realists.
Have you done any looking at transformers, an experience related to insulation degradation / transformer life for units with mineral oil versus silicone versus FR3? Let's not just use FR3. Let's just say synthetic or natural esters.
What's interesting is, and I said that. Well, I think about even the chart that I shared, that the population of transformers that have mineral oil so dwarfs by orders of 10 times, 20 times those other fluids right now, that the analyses would be a bit skewed. And, silicone had a time period with which it was prevalent, 80s, mostly in the paper industry, with the transformers in the paper industry, and now FR3, in the last 20 years. I could always see what we could find, but nothing comes to mind in terms of paper, an insight that we have said, oh yeah, this is specific to the fluid and also, isolated in the paper insulation. There's other, uniquenesses of those fluids, but not specific to the paper.
Looking at
Go ahead,
ways to help those other fluids. Remember, silicone became really popular again for indoor applications. PCBs were in their pure form to be the other way it was done. But silicone, just be really aware that silicone is its own fluid that doesn't like any other fluid. If you make a mistake servicing a silicone unit by either topping it off with oil or with anything but silicone, that you'll ruin the transformer. They're not silicone doesn't play well with any other fluid. We got some charts to show compatibility. Be real careful in service. Silicone's a great fluid. It's very difficult to find. Sometimes it goes through stages where it's hard to buy it, and it gets really expensive. And it's expensive in general. Just it's roughly 4 times the price of FR3, 5 times the price of FR3, and a little bit more than that than the price of oil. So just a little warning there.
All right. Last question, and then we're going to end. You've got, and I hate to use brand names, but we did FR3, so let's do this. What is when you're looking at units that are Nomex insulation, which is a product of DuPont, and it is more expensive. Many people are beginning to use it more often, but how relevant is Furan testing for transformers that use Nomex insulation instead of traditional craft paper?
I think that's related to like the thermally upgraded paper versus the
right.
It's a high end. I don't know that we have data on that, Alan. We could look and ask our lab scientists to look into it. I don't believe I can't answer that unless you can, Wes. I can't.
Okay. No, I mean, I remember us talking about this, like some standard, IEEE has a certain stance on the use of furans on thermally upgraded paper. We think that there's still value, and it gives us good, some good indication, especially when we're considering the price of these tests compared to the information they're giving us. So it's tough to say a test is good or a test is bad. I don't think that's a good characterization as like the value from the test compared to the price of the test. Anyway, yeah.
That is a great way to end this, because one of the things that you've done is you have given what I would consider to be practitioner's standard of how you look at your transformers, look at the data, and then how you service those transformers. Here's the big issue. If you can't get transformers, you better look at the existing fleet and do something about it, because you might be 3, 4, even 5 years out. What has happened in the transformer industry for OEMs, utilities realize they're going to have a problem. Their load is up anywhere from 8 to 10%, which is unheard of for utilities. I mean, they've been running flat for decades, and all of a sudden you got 8 to 10% load growth. So they realized something was going to happen, so they bought slots. That's never happened before. They would go out to OEMs and say, we want 10 of these in 2 years, 15 of these. So the utilities bought up slots. Second in was data centers, especially AI data centers. They then took slots. When the industrials and commercial came along, basically people were sold out from 1 year, 2 year, 3 year. So there is no slot that you can buy into. You can put an order in for price prevailing in 4 years, but that doesn't help you now. So the idea that you're going to decide whether a transformer stays in service, one of the key indicators is that you can't get a replacement. And I've seen it more often than not that people have waited too long. So with that, give us some closing comments, Bob Razor.
Well, I think my summary is where I would end. I've had this has been a pleasure to talk with everyone. It's something that we've seen experientially. It follows science. and it is just useful to extend, and these older transformers, they will last, provided you don't let them get that past that point of no return. So I'd encourage, to look into your fleet and get a nice, good baseline of where everything's at and move from there.
So that point of no return is health index number 4. Is that correct?
Well, in 4, we're still saying investigate. So it's in our data world, it means look at it. It could be, and we just don't want you to not see that it could be. Trouble.
With that said, thank you so much, Bob Razor and Wesley Supplett. Great information. And for those that are still on here, you can get a copy of this presentation. And if we have not answered your question here, we will get these questions to Wes and to Bob, and they can answer through email. Again, this has been an APC Media webinar with SDMyers, Bob Razor, and Wesley Supplett. Again, thank you, gentlemen.